Good morning, Year 12 Specialist Mathematics students, or whenever you are tuning into this lesson. Welcome to our first online lesson today, which will be a good kickstart and refresher on integration. So we're going to look at integration by linear substitution today. But before you get into the video, hopefully that you've completed the warm-up. And also here I have a Word document attached with the solution, which you'll see here. But how this solution is achieved is really by recognition. The purpose and intention of today's lesson and our learning goal will be able to use and apply the change of variable by substitution method to integrate expressions. So I'll start off with the very first worked example today. I'm going to go through 4 worked examples, and hopefully I don't talk all day. As you know, that I easily can achieve that in a lesson. I could talk for 70 minutes. But let's see if I can knock these 4 worked examples on the head, and then you guys can practice some questions today, and always shoot us an email if you want me to clarify any misconceptions or understanding. So the first worked example today, they want us to determine the integral of 2x minus 5 to the index 4 in terms of x. So our very first question here, guys, is looking at our integer n here, which is 4, and in this case we're dealing with our first worked example, which is an element of positive integers, and hopefully you remember that, a little bit of notation. Now, whenever we're doing these integral type questions, you could actually expand this out, but to the power of 4, it's going to become quite tedious. If a question was to the power of 20, you're going to be there all day doing your expansion. So there's little simpler methods which we can do, which is by substitution, which is our topic today. So you might want to actually make your life easier, deliberately emphasize that. And the variable u is commonly used in these questions. So what we're going to do is make all of this in here, 2x minus 5, we're going to make that u. Now, if I was to actually write that out, you would actually see that that would become the integral of then u to the index 4, but we've still got it in terms of dx. Now, what we need to understand whenever we go through our integrations, we need to have our variables essentially here and here. They need to be in the same terms. They need to be talking the same language. So this is probably re-jogging your memory with a little bit of process that we need to get dx. We now actually need to make this. If we're working in terms of u, we need to make this in terms of du. So to get that, we are going to, first of all, we've got u is equal to 2x minus 5. We're going to derive this function. And our notation, hopefully that's coming back to you, is going to be du on dx, and the derivative of 2x minus 5 is just 2. We can rearrange this and get it in terms of dx, which will become du on 2. Now, the purpose and intention while we do that will be shown here right now, that now we've made that 2x minus 5, we've made that u, and remember now we're talking the same language, we want to see things in terms of du. So we've now rewritten the integral by substituting both of those, and now you can look at that and probably say, oh, that's a nice beautiful polynomial type function where we know what the integral is going to be. So in this particular worked example, you've got that coefficient of a half there. Remembering, if you wanted to, you could actually put that coefficient out the front, and that it would actually be 1 over 2, which would then be the integral of u to the index 4, and then again in terms of du. If you wanted to do that and then bring your coefficient back in, that is fine. It's really up to you. You still will come back to the same answer here, which is 1 over 10 u to the integral of 5 plus c. But remember, we need to always write the original integral was in terms of x. So we need to substitute u, which was 2x minus 5, back into here. And that is going to be your completed solution. Our second worked example is going to look at if we had our particular integral function in terms of n, but in this case, n was an element of q. Again, hopefully remember that Q is referring to rational numbers. But the only case we're not going to look at is when n is not equal to -1. That will come in worked example 3. So the second worked example, a few things that I really want you to take note of here is the gradient of a curve is given by 1 over the square root of 4x plus 9. Determine the particular curve which passes through the origin. Now, a couple of things that I want you to note and remember. When it's referring to the original curve, it's wanting us to get in terms of y. And remember, when we derive a function, that's instantaneous rate of change or gradient. So in this case, they've given us the gradient function dy over dx, and we want to get back to the particular curve, which is the original. So just a little bit of language in the question that you need to continually familiarize yourself with. What we can actually also do in this particular question, if we wanted to get it to look like a function to a power of something, we can actually take this 1 over square root of 4x plus 9 and we can manipulate it. Now, if only I could remember how we manipulate these type of functions. One of those particular laws, that's right, index laws. They are a thing. And you might need to revise over that again, but I think I've probably made that joke so many times, you guys know actually your index laws. So when we look at this question, guys, we can take that, the square root, again remembering that that's to the index of a half, and we can raise that to a negative power. So now that we've got our function that looks really quite nice, and it's a function to a particular power, that's not -1. That's the only case where you're not going to look at and go through this process. So once you've got it there, guys, again, this is the same process where you make this particular, so you make that same process, that particular function. So again, you would make that 4x plus 9, let it be equal to u. You would then get it in terms of, and I would do this always in one hit, I would work out du over dx, which is the derivative of that, which is just 4, and rearrange it in terms of dx. Again, you substitute everything back into there, where you'd see that, you'd substitute u, and instead of dx, you would substitute that in. And again, you all know that how to work out your integral rules of polynomial type functions. We are adding 1 to the index or exponent over the new index or exponent and simplifying. So I hope that worked example 2 was quite nice, but there's something else we need to mention in this function. And in this first case, we had a plus c. In this second case down here, we have a plus c. But remember, we can solve for c if we're given another piece of information, which in this question it said, determine the particular curve which passes through the origin. So they give us a coordinate. We know the coordinates of the origin are 0, 0. So when we get to this stage of the question here, and again, we substitute it again back in terms of x, we now can substitute our origin. So we'd substitute y is equal to 0, and in here we would substitute x equals to 0. We would simplify. We would rearrange and solve for c. Once we've got our c, we can then just write our nice completed function there. Or again, you can see that both of those terms are divided by 2. So with the fractions, they have the same denominator, and then we can just add our indices together. So that's the second worked example. A couple of things again to remind ourselves are index laws are a thing. They make our life easier. Integration by substitution makes our life easier as well. And we can also solve for c if another piece of information is given. Our third worked example today, if you note in that previous rule up here, it dealt with rational numbers, but it didn't deal with n being the index of -1. So in this particular question, we are going to look at when n is equal to -1. And I might jog your memory back to mathematical methods when if we had to integrate 1 over x, remember if we were to write that again, that would just be x to the index of -1. So now this is probably coming back to you that this is your, and I've got a graph here of your rational type functions, your hyperbolas that you would have seen. And the integral of 1 over x is ln x when x is greater than 0. But we actually generalize that in our specialist mathematics that The antiderivative of x to the index of n, where n is equal to -1, is ln x plus c. But x cannot be equal to 0. As you can see here, we've got our asymptotes. So here's a particular question we're going to look at. Determine the antiderivative. Remember, these are just all ways that you're going to be exposed to questions. Determine the integral, determine the antiderivative. Notice just the wording of particular type of functions when we come to the exam, your Unit 4 exam, or when you come to your external exams. So note here that x cannot be equal to -4/5 because, again, that's when in this case you're going to have your asymptote. So again, the same process starts when we want to make our life a little bit easier. So we make that denominator u equal to 5x plus 4. We do all the rearranging in terms of the x. Now we get it to the stage of we've substituted again u there, we've substituted dx in terms of du, so we're both talking in the same language. But now that we come to this, again, same process as previous examples. However, when you now determine the integral, you use the rules as mentioned previous. So the integral of 1 over u, the same as 1 over x. Integral of 1 over x was ln x. The integral of 1 over u is ln u. Once we've got that, we substitute it back in terms of x. So hopefully that third worked example was quite nice and easy for us to remember. Final worked example that I want to discuss is definite integrals. Now, if we calculate, our previous 3 examples have been indefinite integrals. We haven't had any upper or lower boundaries, but in this case, they're saying that 1 and 0. I want to make a really big point that we can use our graphics calculator to verify our solution, but really there's going to be, we know that 0.425 is going to be what we're trying to hit as our final target when we calculate or evaluate or determine the cognitions that we're going to see in the questions. But I wanted to also mention that if graphically, what does this question look like? And here, I'll put it again on our TI Inspire. That's going to be from our function, which is really x is equal to 0 and x equals to 1. Now, I want to make a really big point of that. That's actually x is equal to 1 and x is equal to 0. Now, nothing too particularly difficult about this question, but something I wanted to mention that when using substitution to evaluate definite integrals, there is no need to return an expression in terms of x, provided that the terminals are expressed in terms of u. So I've really tried to make that emphasis that x is equal to 1 and x equals to 0. And I want to show you, some of you are probably understanding that. Some of you going, geez, so that's a lot of words. What do you mean? Well, if we take this particular question again, we do the same process. We make our life, or you make your life a little bit easier by you substituting that into there. And you do the same process again. Now, this is the part that I wanted to make a note. You could, if you wanted to, work out when you've got here in terms of u to the index of -2 du. You could work out the integral of that, and like this previous example, you substitute it back in terms of x. In this example in 2, you substituted them back in terms of x. So from there to there. In the first example, again, your final line of working, from there to there, you substitute back in terms of x. Now, in this fourth question, fourth worked example, you could do that. You could go through here and you could actually substitute everything back in terms of x. However, I wanted to show you that you could actually change your upper and lower limits where x is equal to 1 and x equals to 0. You could change that in terms of u. So remember, we made u, which was equal to 3x plus 2. We could substitute x equals to 1 there, and we could substitute x equals to 0 there. So what happens now is we actually get your upper and lower limits here in terms of u. So now with our function, there is no need to change it back in terms of x. Again, we go through and we use our particular notation with our square brackets. We evaluate. And we get the same answer. So just giving you, that's another little tip. Final thing, guys, I want you to read over worked example 5 and 6, very similar. Make a few notes on that, and then I want you to complete exercise 6.2 in these questions. I hope this video has helped. Please shoot us any questions that you have, and hopefully I can answer them. Thank you for tuning in. Look forward to lesson 2.